Okay, so in this podcast, we're going to take a look at what the definition of pH and pOH is, and then some calculations that we can do to figure out pH and figure out pOH.
This is more mathematical, so get your calculators out. So far, we've had the pH scale. You know that low pHs are acids, and it turns litmus red, and high pHs are bases, and they turn litmus blue.
All right, so the pH scale is actually a logarithmic scale, and what that means to us is that every change in one pH, so going from 1 to 2, is actually a change in 10 times the concentration of either the hydrogen ion or the hydroxide ion, depending on which way we're looking at it. So if it's a pH scale, we're looking at hydrogen. So if we went from 1 to 3, now there's a 100-time difference between 1 and 3.
But there's only, wait a minute, there's only a 2-number difference.
That's right, because it's a 10-time difference for each number.
Okay. So 2 is 10 times bigger than 1.
Right.
And 3 is 10 times bigger than 2.
And 10 times 10
is 100.
Yes.
So 1 to 3 is 100 times stronger. That's kind of like the earthquake scale, isn't it?
It's the exact same type of scale. It's a logarithmic scale, just like that Richter scale for earthquake.
But look at this diagram here. This one's on the front of your packet. This is kind of conceptually what's going on inside the solution. There are, even though the picture on the left has a low pH, there's a lot of hydrogens, because that's our acid. That's acidic. But notice there's this one hydroxide.
Yeah, so even though it is a low pH and we consider it acidic, there are still ions in there that we would find with a base.
But
it's just that there's more of the acid ions than there are of the base ions.
It's like a competition. There's more acids than bases, so it's acidic.
And clearly the hydrogen here is winning.
And on the right side, it's backwards.
The hydroxide's now winning.
There's a lot of hydroxides. There's one little acid particle. So this side, if we were to look at that solution, that is basic, and it has a high pH. So again, explaining that picture, if we have more hydrogen than hydroxide, it's acidic with a low pH. And if we have more hydroxide than hydrogen, it's basic with a high pH. That's very important because both of them exist in all the acid-base solutions. We're going to need to calculate those concentrations, though. These brackets here that you keep seeing, that represents molarity, which is a concentration.
pH is the power of hydrogen.
That's the power of hydrogen. That's the power of hydrogen.
So it's how strong the hydrogen is in an acid or in a solution.
So the equation here to measure pH, it has to do with concentration. The pH, it's a logarithmic scale. If we take the negative log of the concentration, we will get a number somewhere on that pH scale that tells us how acidic it is based on how much concentration of hydrogen there is. Or hydronium, because they're interchangeable with each other. So a 10.0 earthquake
is 100 times greater than an 8.0 earthquake.
Crazy.
Yeah. Which is why that earthquake in Japan was so devastating, because, a 9 or whatever it was is ridiculously strong.
pH. Let's get some practice problems with pH. Get your calculators out. Make sure you can calculate these along with us. It really is an equation. You need to know that the pH is the negative log of the hydrogen concentration. And these are always going to be in scientific notation because the concentrations are really small in solution. So for this one, hydrogen molarity of 1.0 times 10 to the negative fifth, that's a molarity. If I take the negative log of that...
So on your calculator, you're just going to hit the negative sign, hit the log button, and then within the parentheses that it gives you, just like is being written here, you can put this 1.0 and then hit second comma, which is where the EE resides, -5, and your parentheses.
That EE puts it in scientific notation. Remember that button, so you don't have to type in times 10. It's just EE, that means times 10 raised to the negative fifth power.
Hit enter.
Go ahead, put that in, get enter, and you get a pH of 5.0. Now, is that acidic, basic, or neutral with a pH of 5?
pH of 5, let me think. That's acidic.
That's
below
acidic.
7.
Below 7.
Yeah.
Do it again, negative log of 3.30 times 10 to the negative fifth molar. You put that in your calculator, and you should be able to get 10.5, which is greater than 7, and basic. Make sure you can get these values in your calculator. If you're not getting them, keep trying.
I noticed that both of those problems, one of them says with the brackets around the H+, and one of them's the brackets around the H3O+.
That's true, but they mean the same thing. They're both acids, hydronium and hydrogen.
So some practice problems now calculating the concentration of the hydrogen ions or the hydronium ions.
There's a new equation for this. It's really the same equation rearranged if you know how to use logarithms. If not, you can just remember it.
The inverse function.
It would be
of the logarithm.
It would be the inverse log. But if you rearrange that first equation, you get the hydrogen molarity equals 10 raised to the negative pH. So this helps you find the concentration if you have the pH.
This is actually even simpler than the last calculation we just did.
But take a look at your log button on your calculator. Right above it, you will see that 10 to the x. That's the inverse log button.
Hey, that's convenient.
Which, hey, right there, 10 to the x, pH is x, 10 to the x. So try and use that button, hit second log, and you'll get that 10 to the x to pop up. So if you hit second log, you'll get 10 to the negative 12.3. You'll get the molarity of the hydroxide. And if you put that into your calculator, you should get a concentration of 5.01 times 10 to the negative 13th power.
You meant the molarity of the hydrogen, right? I think you said molarity of hydroxide.
Did I? It's the hydrogen.
Okay.
It's definitely the hydrogen. And with a pH of 12.3, that definitely sounds like this solution is basic. It's higher than 7. Nice. pH of 5.4, let's start out calling that one acidic, less than 7. Again, second log, you'll get the 10 to the negative 5.40. Put that into your calculator and you will get the hydrogen molarity, which is 3.98 times 10 to the negative 6th. Big M. I should label these because they have their molarities.
So you can see why we use pH when you look at these numbers we're calculating. It's hard to tell if that's acidic or basic. So the pH scale makes it really simple for us to make a quick judgment. Is this less than 7? Is it more than 7? Or is it right at 7 and neutral?
Whoa, pOH. What are you doing? What is that?
Well, if pH is power of hydrogen, it looks like then pOH would be the power of hydroxide.
Okay, this equation seems pretty simple. Subtraction, I can do this in my head. Addition, subtraction. If I have a pH of 6, I have a pOH of 8. Hopefully you didn't put your calculator for that one. So, is this acidic, basic, or neutral?
Well, if you look at the pH, it's a 6, which is less than 7.
Okay, so that one tells me it's acidic.
It's acidic.
Okay, but the pOH is greater than 7.
Yeah, and we said if the pH was greater than 7, that it's a base.
Yeah.
But for the pOH, if it's greater than 7, it's actually the opposite. So if the pOH is greater than 7, it's acidic.
So it's backwards.
It's backwards.
Can I just look at the pH?
You could.
Okay, so pH less than 7, it's acidic.
Which is kind of why this formula comes in handy, because we'll try to throw you off and give you some pOHs and say, is this acidic, basic, or neutral? And once you're armed with this equation, all you have to do is calculate the pH and it makes it real easy.
pH lets you know if it's acidic, basic, or neutral. pH of 6 is acidic. pOH of 6 means my pH is 8. All right, now I think I'm catching on. The pH is 8. That means this one is basic because the pH is greater than 7.
Yeah, you got it.
And if the pOH is 7, that means
14 minus 7. So 7.
That is 7.
Okay.
They're equal.
Nice. That's neutral.
There is this third option. If they're equal, the solution is neutral because they cancel each other out. There's an equal amount of both hydrogen and hydroxide ions. They're equal molarities. It's neutral. Next slide. Get out the pen. Well, just like with pH, we can talk about pOH concentrations and hydroxide. It's the same two equations with a different label because now we're talking about bases. So, if you know one equation, you know this one as well. You just need to keep the label straight. pOH is the negative log of the hydroxide. So if I have my molarities here, negative log of this molarity, You can put that into your calculator like we did before, and that'll give us a pOH. So my pOH for this is 5.6. Is that acidic, basic, or neutral?
Well, if I subtract 14 from that, right, that can get me the pH.
That'll get you the pH. It will. Can you do that in your head?
Sure, 8.4.
All right, we'll pretend we did that in our heads. 8.4, which on the pH scale means basic. We can do the same thing with the second problem. We get a pOH if we take the negative log of that concentration. That pOH is going to be 1.1. And is that acidic, basic, or neutral?
I'm going to guess that's really low on the pOH scale, so I'm going to say that's a base.
Because the pH scale, that's 12.9.
Yeah, I was just going to say, I knew if I subtracted that from 14, I'm still going to get a really high number for my pH.
I wrote down acid. That's wrong. pH scale is high. That's basic.
Nice.
Basic is good. The hydroxide, we can do the same thing. Solving, if we have the pOH, we can get the molarity.
So we need to recall what our formula is. It's up on the top. Just like the pH formula, 10 to the negative pOH gives us the concentration of the hydroxide ions.
And remember, that's your inverse log function.
Yep.
So inverse log, you get 10 to the negative 4.5. My concentration is going to be 3.2 times 10 to the negative fifth molar, and that's my hydroxide concentration. Since I have pOH, the OH hydroxide goes together. Is that acidic, basic, or neutral?
pOH is 4.5. If I subtracted that from 14, that's going to be greater than 7.
I think it is. It's going to be 9.5.
So
that means it's a base. Second problem, pOH of 7.9. 10 to the negative 7.9 gives me a hydroxide concentration 1.3 times 10 to the negative eighth.
And then if
That
we
is
want
an
to
8.
figure out if that is acidic, basic, or neutral, subtract
Get
7.9 from 14.
Get the pH,
That is
6.1.
less than 7, so it's an acid.
Acidic. All right. So 4 equations, but really only 2. You just got to keep the label straight. Acids go with acids. Bases go with bases. All right. So now that we have the pH, we've talked about pOH, hydrogen concentrations, hydroxide concentrations, we can put them all together here with this little bridge analogy.
So you can see connecting pH to pOH is the fact that pH plus pOH equals 14. So using that, we can go from calculating maybe a hydrogen ion concentration to perhaps finding the pOH of a substance.
Correct. And just you got to remember with this, the acids go with the acid equations, bases go with the bases equations, and the only way between them here, pH and pOH, will get you across the bridge so you can talk about acids and bases together. Let's do a quick example here showing multiple steps. If we have a pH of 14, if we have a pH of 7.4, what is the hydroxide concentration? Notice here my pH is talking about an acid, and I'm looking for a base.
Okay, so our first step to solve this problem is going to be going from pH to pOH, because pOH is the only thing that we can use to get the concentration of hydroxide.
Because they're both bases, the OH and the OH. If my pH is 7.4, that means 14 minus 7.4. My pOH is what?
7.6?
I don't think it's 7.6.
No, it's definitely not.
6.6?
Try.
6.6.
Wow, that's
we were
embarrassing.
legitimately confused there. 6.6 is my pOH. Now that I'm over here at my pOH, I can use this equation. I can have my pOH. I can get my hydroxide concentration.
Yeah, so we just need to do 10 to the negative 6.6. And that gets us the concentration of the hydroxide.
So 10 to the negative pOH gives me 2.5 times 10 to the negative 7th molarity, and that is my hydroxide concentration, which is what we were looking for in the problem.
Awesome.
Now, with all of these, we've been asking, is it acidic, basic, or neutral?
Wait, the pH is 7.4. This is an easy one. That's
Yeah.
greater than 7.
pH, that's the one that tells us.
Yes.
pH greater than 7. This solution is basic. Last example, if I have a hydroxide concentration of 3.4 times 10 to the negative 6th, what is the hydrogen concentration? A little bit more work here because I have my hydroxide, but I need to get it into pOH to get across the bridge.
All right, so our first step is going to be to figure out what the pOH is from the hydroxide ion concentration.
And that's negative log of that hydroxide, 3.4 times 10 to the negative 6th. My pOH, if I plug that in, is 5.5.
Okay, so once we have pOH, then the next step we can take is to get from pOH to pH.
And if I subtract that from 14, I can get 8.5.
Great.
Is a pH.
So when we have pH, then the final step would be going from pH to the hydrogen ion concentration.
Using the equation 10 to the negative pH, or 10 to the negative 8.5. Put that into your calculator, and you should be able to get a hydroxide concentration of 3.16 times 10 to the negative 9th molarity. That is the answer to our question. And the follow-up question, is it acidic, basic, or neutral?
Well, if you look at the pH, 8.5, greater than 7, that's basic.
Basic. That's pH and pOH. Those are the basics.